In this video, we discussed limit definitions of the derivative and the slope of a curve at a point. So here's the idea. Let's say we've got y equals f of x. Maybe it looks like this. And we're interested in the slope at this location. Just going to call that x naught. The function value there, I'll call f of x naught, because at least in this picture, it happens to be continuous. And our goal is to find the slope at that location. It's basically what we're looking for is the slope of what we call the tangent line. That's a line that has the same slope as the curve. I know that reasoning is a little bit circular. Sorry about that. The slope of the curve and the slope of the tangent line at a particular location are basically the same thing. And we're trying to find just the slope of that line. Now, if we wanted to find slope in general, the slope of any line, it's just going to be the change in y divided by change in x. Sometimes we say rise over run, but I'll say rise or fall over run, depending on whether delta y is negative or positive. If the point x1, y1, and x2, y2 are points on our line, the slope is just given by the difference between the y values, that's their change in y, divided by the change in the x values. So if I have a particular line, let's actually do it like this. Here's x1, y1. Here's x2, y2. You can visualize that slope this way by making a triangle. This distance here is the larger y value minus the smaller y value. That's y2 minus y1. And this distance here is the larger x value minus the smaller x value. So that's going to be x2 minus x1. So this is our rise or fall if the line was going decreasing as we go from left to right. And this is how much we're running. So we want to use this idea right here, but the problem is if we talk about the slope at a particular point, x1, y1 and x2, y2 are the same point. So what I'm going to end up with is a 0 over 0 indeterminate form. But we can just look at this line and we can tell it has a well-defined slope. If I knew what the units were in the x direction and y direction, I'd be able to calculate the change in y just by measuring it and calculate the change in x just by measuring it and divide, and I would know what the slope of that line is. So you might say, how do you find the slope of a line in general? Well, we start by graphing this point, and then we graph a neighboring point. So let's say we've got a point over here. And let's take a step delta x units to the right of where we were. So this is x naught, and this is x naught plus delta x. A line connecting those 2 points is called the secant line to the graph of the function. And we find the slope of that line, and I'll represent that by m sub secant equals change in y over change in x. And so that's just y2 minus y1 over x2 minus x1. And in this case, y2 is the y value at x equals x naught plus delta x. So that's f evaluated at x naught plus delta x. And y1 is just f of x naught. So we substitute those in. And this kind of looks like alphabet soup, but it's not. It's just f evaluated at a particular expression minus f evaluated at x naught. It's just 2 y values. It's just one y value minus another. And then x2 minus x1, if this is my x2 and that's my x1, is just x naught plus delta x minus x. And because we're subtracting, the delta x is reduced, and you just get delta x, which makes sense. That's our notation for the change in x. how much did X change as we went from here to here? Delta X units. So it makes sense that it would simplify to just being that. You say, okay, well, how do I find the slope of the graph at this point? Well, if I call this point P and I call this point Q, what we do is we take this point Q and we move it. We get another Q that's closer to P, and then another Q that's closer to P, and just a sequence of Qs. And we let the Qs get closer and closer to P, and we calculate the slope of the secant line every time. It turns out in the limit, as this delta X approaches 0, so those 2 points are getting closer and closer together, and the slope of this line will approach the slope of that line. You might say slope of that line, well, not that particular line, but that slope of the sequence of secant lines, the slope of the secant lines in general, will approach this line right here. So that maybe that's my Q1. I'll call this Q2 and draw another secant line. And then we'll draw another secant line over there. And now remember, you're talking about the slope of these lines. You can see geometrically that these lines, these blue lines, are approaching the red line. But each time we're doing that, we're calculating the slope. So this is going to have a small positive slope. This one's a little bit steeper, so this slope is a little bit larger. Then the slope is a little bit larger, and then we have the slope over here, which is larger. And in the limit, as these points get closer to that one, the slope of all of these lines approaches the slope of that. So if we want the slope at this location P, then we can say that that's the slope of the graph at x naught, or if you prefer, you can say at x naught, f of x naught is equal to the limit as delta x approaches 0 of f of x naught plus delta x minus f of x naught divided by delta x. And sometimes this is called just the slope of the tangent line at x naught. And of course, it's the slope of the graph of y equals f of x at x naught, the slope of the tangent line of y equals f of x at x naught. It's specific, it depends on the particular function. And that's equal to that. And it's super easy to calculate. And this is actually the definition of what we call the derivative of f at x naught, denoted f prime of x naught. That's one of our notations. And they're all the same thing. So geometrically, this is what we're calculating. And this is how we do it algebraically. And this is the shorthand notation for that. All right, so let's look at an example. Let's use f of x equals x squared plus 2x minus 3. And if I complete the square, I'm going to add 1 here to make that a perfect square. And that's legal as long as I also subtract 1 there. And I'm just adding a well-chosen 1. This expression is x plus 1 quantity squared. A negative 3 minus 1 is negative 4. So I see that I've got a parabola. And if I write it in this form where I've completed the square, it's obvious what the vertex is. The vertex will occur at the x value that causes this expression to be 0, which is negative 1, and the y value that we get when this expression is 0. So y will equal negative 4. So the vertex is at location typically denoted by h and k, given by the x value that causes this to be 0, which is just the opposite of this number, negative 1, and k equals negative 4. That's not right.
I bet they.
So this is our parabola. Now we might be interested in finding the slope of the graph or the slope of the tangent line to the graph at x equals x naught for a particular value of x. What's nice about this is that this was derived using a particular value of x, but we could just as easily replace x naught with x. And then what we end up with is a formula for the slope of the graph. So you do this computation, you'll take the limit as delta x goes to 0, and then you're going to have a function of x. And that function of x will allow you to find the slope anywhere in the domain of the original function. So let's do that. Let's find f prime of x, and then we'll use that to compute the slope at a number of points. That's the limit as delta x goes to 0 of f evaluated at x plus delta x minus f of x, all divided by delta x. And all I've done is change the x naught to x so that we get this formula for the slope. Now it's probably easier to see what the how the numerator simplifies if we use this expanded form of f of x. So let's look at the numerator first. We want f of x plus delta x minus f of x. Probably should have done this first in a different color. Now f of x plus delta x just replaces all of these x's with x plus delta x. So you're gonna have whatever the input is squared plus 2 times whatever the input is minus 3. And then you're going to subtract the entire function evaluated at x, which is just x squared plus 2x minus 3. Here I'll replace x with x plus delta x. That's x plus delta x times x plus delta x. If we distribute the 2, we'll have 2x plus 2 times delta x, subtracting 3. Then we're subtracting this polynomial, so we'll distribute a -1 to all of the terms there. Just multiplying by -1 and with a polynomial just means you can change the signs and add like terms. So we'll have a negative x squared, and then a negative 2x, and a positive 3. And that's in our numerator. We can finish writing this out here. First times first is x squared, outer times outer is x times delta x, inner times inner is just like it, so we've got 2 of those. Last times last is delta x quantity squared. And of course, we could simplify this first before we substitute it in if we want to. The -3 and the 3 reduce. And this x squared and negative x squared reduce. And the positive 2x and the negative 2x reduce. So f prime of x is the limit as delta x approaches 0 of that numerator, which is this 2x delta x plus that delta x quantity squared plus 2 times delta x, all divided by delta x. Now notice if we substitute in delta x equals 0, we get 0 divided by 0, which is actually, again, what we would expect if we're using this formula for the slope, and x1 and y1, or x1, y1 is the same as x2, y2. We're starting at one location, like subtracting the y's from themselves always gives 0. The same thing with subtracting the x's. So when we substitute delta x equals 0 here, we always have a 0 over 0 indeterminate form. But we can get rid of it in most cases. To do that, we will look at that numerator and factor out any common factors. We see that they all have a delta x in common. This one has a factor of delta x, that one has 2 of them, and then that one has the delta x as well. So you can factor that out. You say delta x times what gives us the 2x delta x, just the 2x. Delta x times another delta x gives us that middle term. And delta x times the 2 gives us the last term. We're dividing by delta x. And then we're taking a limit. Now, because of everything that we studied in the previous chapter, we know that as long as any quantity is not equal to 0, we can divide it. Like 1 divided by 1 is 1, 3 divided by 3 is 3. Delta x divided by delta x is 1, as long as delta x isn't 0. And remember, we're just taking the limit as delta x approaches 0. So whenever we compute the limit, delta x isn't actually 0. We're just getting very, very close to 0. This might be 0.00001 divided by 0.00001. It's just the same number, and they're both positive or they're both negative. They're the same, and so we can cancel those. So we reduce that. We're using that factor and reduce method that we talked about in the last chapter. And then we say, okay, is the resulting function continuous at delta x equals 0? Can we just substitute in delta x equals 0 here? And it turns out that we can. If we substitute in delta x equals 0, we get a 2x here, plus 0, plus 2, which is just 2x plus 2. And what this is a formula for the slope of y equals x squared plus 2x minus 3. Add any x in its domain, which is just any real value of x. So when x equals 0, the slope is 2. When x equals 1, the slope is 4. When x equals -3, we get 2 times -3 plus 2. That's the slope. So this is just telling us what the slope is in general. We could have used this formula for a particular value of, or this formula here for a particular value of x naught. We could say, oh, I'm only interested in what happens at x naught equals 2. And you could plug in x naught equals 2 and do all of this calculation. But I like this better because this gives us an answer that works for all x values, all x in the domain, and not just one particular value. Once you have that formula for the slope, you can plug in any x value in the domain and it will give you the right answer for the slope. So now that we know that that's the formula for the slope of this particular function, we can answer a couple of other questions. We can find the slope at various x values at x equals, let's say -3, and at x equals -1, and at x equals +1. And if we've drawn our graph to scale, we can confirm that those slopes are correct by graphing not just the curve, but also the corresponding tangent line. So the slope at x equals 3 is just, oops, sorry, that's not a good way to write it. Let's just say f prime of -3. That's the slope at x equals 3. I keep saying 3, -3 is 2x plus 2 evaluated at x equals -3. So 2 times -3 plus 2 is -6 plus 2, which is -4. So we know that the slope there is -4. And with the slope and this particular x value, we can find the corresponding y value, and then we'll have a point and a slope, and so we can find the equation of the tangent line at that location. Let's find the slope at the other points first. Let's plug in x equals -1. It's going to be 2 times -1 plus 2. Happens to be 0. Let's find the slope at 1. So 2 times 1 plus 2, which is 4. And if I draw a tangent line here, At x equals -1, that tangent line is horizontal, so it has a slope of 0. That's exactly what we would expect. At this location, the slope is supposed to be -4. Say, okay, well, maybe it is. Let's find out what the tangent line is and graph that along with our curve and make sure that it's tangent to the curve. It looks like it is. And then at x equals 1, we have a slope of +4. I didn't mean to choose points that were an equal distance from -1, but I guess I accidentally did. And because of symmetry, we get the -4 and then the +4 there. So yeah, we're gonna have those are the expected slopes. So we can now find the tangent lines at each of these locations, graph those, and see if they're actually tangent to the curve, which will allow us to determine whether our answers are correct and whether our formula for the slope, this f prime of x equals 2x plus 2 actually makes sense. So let's do that. Oops. And then the y value at x equals -3 is f of -3. We've actually already found that value. It was 0. Just using that sort of known relationship between the points on a parabola with an a value of 1. But we can also find that just by doing the arithmetic. So we have -3 squared plus 2 times -3 minus 3. So we have 9 minus 6 minus 3, which is 0. So the point x naught, y naught on the tangent line is x equals -3, y equals 0. And now that we've got that point and that slope, we can use the point slope form of the equation of a line to write and then simplify the equation of the line. Since y naught equals 0 and m equals -4 and x naught equals -3, that's our equation. Subtracting a negative is the same as adding. And we'll distribute the -4. And so we have y equals a -4x minus 12. So the y-intercept is -12 and the slope is -4. It's a little bit hard to see. That's the tangent line right here. So if I kept graphing, the question is, would this line cross the y-axis at y equals -12? I don't know. I mean, I don't even have enough room for y equals -12 to y equals -4 right here. But I can use a graphing calculator to graph that line now that I've found it by hand, and we'll graph this function as well. Let's find the tangent lines at the other 2 points. So the slope again is f prime at -1, which we found using our formula, which happened to be 0. And f of -1 is -1 squared plus 2 times -1 minus 3. So I've got 1 minus 5, which is -4. So I'll point x naught, y naught on the graph is x naught equals -1, y naught equals -4. And then we'll use a point slope form of the equation of the line again. Super simple, very easy. And the slope was, in this case, 0. I have 0 times something, which is of course 0. I have y plus 4 equals 0, which corresponds to y equals -4. So it's a horizontal line. And if we look at our graph, that's consistent with our picture. When we wrote our function in this form by completing the square, we knew that the vertex would occur at x equals -1, y equals 4, or -4. So y equals -4 should be the slope of the tangent line there, which makes sense to us. And then we'll do this again at x equals 1.
Sorry.
So we have 2 times 1 plus 2, so 4 is the slope. Then f evaluated at 1 is 1 squared plus 2 times 1 minus 3, which happens to be 0. So x naught, y naught equals 1, 0 is a point on our tangent line. It's also a point on the curve. And so the equation of the tangent line can be found using point slope form and then simplifying. We just have a tendency to solve for y. So that's our equation. Distribute the 4. And y minus 0 is, of course, just y. So y equals 4x minus 4 is the equation of the line. And if we graph that, that seems consistent with the graph that we drew. This line does seem to cross the y-axis at y equals -4. So let's graph those on Desmos.com and make sure that it's the answer that is consistent with our picture here. Okay, so I started recording and then I started getting rid of the graph, sorry. So this is our parabola. F of x equals x squared plus 2x minus 3. The y-axis is right here, and the x-axis is right there. It's a little bit hard to see. I'm going to change the grid, maybe get rid of the grid for now. Well, actually, maybe get rid of the minor grid lines. There we go. Makes it a little bit cleaner. But this is our function. We completed the square to show that that was equal to another function, or actually the same function in a different form, x plus 1 quantity squared minus 4. And if we graph that, look, they overlap, they're the same. So I've got that. And then we calculated some tangent lines on paper. So first we said, okay, I'm interested in the tangent line at x equals -3. So we found the corresponding y value. We computed the derivative using the limit definition, which we all did all of that on paper. And then after we found the derivative and we had this point, we used point slope form of the equation of the line to find the equation of the tangent line. Remember, the tangent line is supposed to have the same slope as the curve. From our computation, the line equation of the line is y equals -4x minus 12. And if we look at it, it does seem to intersect the y-axis at y equals -12. It looks like it's got a slope of 4. So we go, or -4, we go down 4 and over 1. Just if you just pick 2 arbitrary points on the line, you can see that it has the right slope, and it just sort of hugs the curve. It's sort of tangent to the curve at that location. So it looks like we did our calculations correctly. Now we're also interested in the tangent line at x equals -1. That was actually the vertex of our curve. So maybe I should change the tick marks here. Don't know if I can do that. I know I can do that. I just don't remember how to do it. No, it's not going to help. Let's do step size of 1. There we go. And step size of 1 for the y's. Oh, maybe now that's too dense. Okay. But the whole point was just to show you, whoops, I'm having trouble moving that little box. That the vertex occurs at x equals -1, y equals -4. So we're right there. And we're interested in the tangent line at that point. Well, it looks like, since we're at a minimum, the tangent line is horizontal. So I would expect the equation of the tangent line to be y equals -4, because that's the function value there, and that is consistent with our limit definition of the derivative, and then evaluating that limit definition, or evaluating that formula for the slope at x equals -1. We did all of that on paper. So we've got that line right there, and it is tangent to the curve, so we know we did our calculations correctly. And then we are also interested in the tangent line at x equals 1. So we plot that point. When x is 1, y happens to be 0. we find the derivative, was 2x plus 1 or 2 in general. At x equals 1, the slope was 4. And we found that again using the definition, the limit definition. So then we use point slope form of the equation of the line to find this equation. And that line y equals 4x minus 4 is tangent to the curve, and it passes through that point. And we can tell it's tangent because it has sort of the same slope. Let's do that as the curve at that particular location. Now that we're familiar with the limit definition, I'd like to use technology to help us visualize this, make sure we understand the concept. So I wanted to make a graph that was pretty on Desmos.com with lots of hills and valleys. So just by manipulating coefficients and subtracting different values from x to get our function in a particular region, I came up with this ridiculous function. It was actually something involving an x minus 3 to the 5th and an x minus 3 cubed. And eventually I just distributed everything and I got all of these crazy coefficients. But it's really just a simple polynomial. It's just a constant times x to the 5th plus a constant times x to the 4th and so on. And we know that the derivative of this function at a particular x value is given by this. Now, Desmos.com does not like this delta symbol. It doesn't give us the option to use Greek letters, not at this time. So we're going to use H. That's another common notation rather than delta x. So instead of using x or x naught and delta x, we're going to use x naught and H. So I have f of x plus h minus f of x divided by h. And if we're interested in this at a particular value of x, and we will use a particular value of x, at least in the demonstration, we'll use x naught here to represent a particular value. And then we'll be able to change the code a little bit so that we can vary that x naught later. But let's look at the graph of this function on Desmos.com, and then we'll talk about using this definition. And we're going to use this form just to match the notation that we are using on Desmos. Oops. All right, trying to get this sort of bar out of the way now. Let's see. There we go. Okay, so here's our graph. I think I'm gonna get rid of some of these things. So this is our graph. And again, I just made up a function that had some interesting points on it. And I'm interested in the slope of the function at this location. X equals 2.25. Y equals f evaluated at 2.25, which I don't remember what it is. Okay, it's giving me, this should be a point, not a, there we go. It's about -4, which is consistent with what we see on the picture. Where did that other point come from? Oh, okay. All right. So we're interested in the slope at that particular location, just for right now. Okay. That's the function value there. Now, typically we would use the limit definition and substitute x naught equals 2.25 to compute this, to compute the slope of the tangent line at that location. It's a little bit tedious because we've got this function involving an x to the 5th, but it turns out that there are shortcuts that we'll learn in a little bit in the next few sections. But let's do a little bit of this on paper. All right, so we're going to visualize the limit definition of the derivative for a particular function, and this is our particular function. f prime of x naught is defined this way. And because delta x is not something that we can type into Desmos.com, Desmos.com doesn't like the Greek letters, we're going to use h instead of delta x. So we're going to use the limit as h approaches 0 of f of x naught plus h minus f of x naught divided by h. In this case, x naught is going to be 2.25 just because of our picture, just because it was a nice point where we could find the tangent line. We're going to substitute 2.25 and h into that function, subtract f evaluated at 2.25 and divide by h. To actually do this, we do all of this over here. So we take this 2.25 and we plus h, and we replace every x with 2.25 plus h. So initially I just wrote -2 times some open parentheses to the fifth, and then I plugged in that x value. And then this is 30 times x to the fourth. So I'm going to have 30 times open parentheses to the fourth, and then I plugged in that x value. So when I write this down, I just open some parentheses as a placeholder for whatever I'm going to put inside. And then I put those inside functions inside, and then we simplify this. Now we can simplify this using what's called Pascal's triangle, which is right over here. We start with a couple of ones at the top. You get a 1 and a 1 and a 1. And then you bring the ones down on the sides and you add the digits in the middle. So 1 plus 1 is 2. And then you have a 1 and a 1 over here. And then 1 plus 2 is 3. And 2 plus 1 is 3. Then you bring the ones down again. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Then you have the ones on the outside, add these to get 5, add these to get 10, add these to get 10, add these to get 5, and so on. Now, these are the coefficients of a plus b raised to the n power. Now, those powers or those coefficients multiply two factors is a to some power times b to some power, and those powers add together to give us that exponent right there. So if I'm looking at a plus b to the fifth, which is what I'll be evaluating right here, basically my first term just has an a to the fifth times b to the 0. There's just the one term. And then the powers of a will decrease as you go from left to right. So you have a to the fifth, a to the fourth, a cubed, a squared, a, and then an a to the 0. And then as you go from right to left for the b's, you have b to the fifth, because that's an a plus b raised to the fifth. Then you have a b to the fourth, b cubed, b squared, b to the first, and the b to the 0. And then the coefficients of those terms are just given by the 1, the 5, the 10, the 10, the 5, and the 1. So those are our coefficients. Now I want you to notice that if you've got an a to the n times, or a to some power times b to some power, those powers are always going to add up to 5. So that's how I know, or how I knew what this was. I knew I would start with an a to the fifth, and then I knew I would have a 5 from here times a to the fourth. And then I said, how many b's do I need so that I have a total degree of 5? So that's just an extra 1. So then I took the next coefficient, which was 10, and then I said the powers of a have to decrease. So I have an a cubed. How many b's do I need so that the total degree is 5? 2. And so then I have an a squared times b cubed, a to the first times b to the fourth, and so on. And so it makes a nice pattern. So if I want to evaluate this expression now, I plug in this 2.25 plus h for all of our x values. And then I use this, this is what's called the binomial. I'm just going to call it a binomial expansion for this a plus b to the fifth. I expand it using Pascal's triangle. And I do that for this one, and then I do that for this one, and this one, and this one, and then this one. We distribute. After we distribute, we collect like terms. We've got a number here. We're going to have basically a polynomial in h plus a constant. And that's what's going to go right here. And then we're going to subtract f evaluated at 2.25, which is just a number. And when we are done, all of the numbers are going to cancel. And we're going to have a factor of h in every term. You factor that h out, the h is reduced, and then you'll be able to substitute h equals 0. When you do, that's going to give you the slope of the function at x equals 2.25. So that's the plan. That's what it's doing. It's not exactly what the computer is doing, but it is the definition of what the computer is doing when it's computing that f prime of 2.25 for us. But that's how we compute the slope of the curve given by this function using the limit definition at 2.25. So let's visualize that on Desmos.com now. So we've graphed the function and our point, x naught, y naught. So that's 2.25 and the function evaluated at 2.25. That's that point right there. And then we're going to graph the tangent line at that location. So if we evaluate f at 2.25, we find that the y value is approximately negative 4.05 or negative 4.06, which is right there. And then if we want to find the slope of the tangent line, we just use the calculator on Desmos.com to compute that slope. We'll say m subtangent is f prime of 2.25. And when Desmos does the calculation, it tells us that the slope is 6.96 approximately. Now the equation of the tangent line is given by this. We have y equals y naught, so that's our original y value, f of 2.25, plus the slope of the tangent times the change in x. So it's basically saying you take the slope, which is change in y divided by change in x, you multiply by the change in x, and then you add the original y value to find the new y value. And so that gives us this. And again, we know that the slope is 6.96 approximately. Now, to help us understand this limit definition of the derivative, we also want to visualize the secant line at a nearby point. Because Desmos doesn't like delta x, we're going to use h. So I added this slider for h. And then we'll have Desmos plot the point on the curve given by 2.25 plus h and f evaluated at 2.25. And then we will find the slope of the secant line, which is just change in y over change in x, which is f evaluated at 2.25 plus h. So at the second point, minus f of 2.25, so that's our change in y, and divide by the change in x, which is that distance, that horizontal distance between those 2 points, which is h. And we see that the slope of the secant line between these 2 points is approximately 3.32. The equation of the secant line is just the same as the equation of the tangent line, but rather than using the slope of the tangent, which came from the derivative at 2.25, we use this slope. So we have the original y value plus the change in y over change in x times the change in x. And that gives us this graph. Now, again, we already know the slope of the tangent line is about 6.96, and we have the slope of the secant is 3.32. So now we can think about what happens as delta h goes, or delta x goes to 0, which is saying that h goes to 0. It's easier to see if I sort of drag this little piece right here. So let's let h get closer and closer to 0. And look at what happens to the slope of the secant. The slope of the secant is changing. So initially the slope is about 3.8 right there. Now the slope is a little bit less than it was before. It's less steep, so the slope is about 2.97. Here the slope starts to get steeper again, so it's 3.39. And then as h goes to 0, you can see that the slope of the secant and the slope of the tangent are almost identical. Now, h can't be 0. If h were equal to 0, we'd be dividing by 0, and that's not allowed. So the slope of the secant is undefined. But as h gets very, very close to 0, we see that that slope of the secant approaches the slope of the tangent. So those are the same things. Now you might be saying, what if I don't care about 2.25? What if I'm interested in a different x value? Well, in that case, we can change our code just a little bit. We can replace this 2.25 with a. Let's add a slider for a. And then I'll evaluate my function at a. And let's restrict ourselves to the interval. Let's say 1.8 to 5.5. Just we want x values that we can actually see on our graph over here. And we'll evaluate f at a. So we plotted. I'm going to get rid of these other lines for right now.
most of them probably
So that's
know what's happening.
A and F of A.
Need to grab those very like.
A is 1.8, F of A is negative 7.39 approximately, which is consistent with our picture.
You'll be okay.
We can see it a little bit better if we add some grid lines. I personally don't like adding too many grid lines. I think it makes it messy. But if this is -5, then that's about negative 7.4, which is consistent with the calculations here. Then I can find the slope of the tangent line at that location, which is about 5.184. And then instead of using F of 2.25, I can replace 2.25 with A and graph that line.
And they'll kind of map it out and they kind of do what they need.
Now, in order to visualize what we're doing, we can graph A plus H and F of A plus H, second point on the graph.
Any family photos beforehand.
And we can let H change. The slope of the secant, we'll use A here and A here. Normally I would use X naught, but again, the calculator is a little bit funny about what it uses for its variables. So I'm just gonna use A rather than X naught. I'll graph the secant line there. And there's the slope of the tangent and the slope of the secant line. And now we can change that for different values of H and different values of A. And it's easier to see if we take these little sliders and move them all to the same sort of area on the left sidebar here. So as H goes to 0,
Oh, nice.
our secant lines approach our tangent line. And look, check out the slope of the secant. It's approaching that 5.84.
Originally.
Now it's varying,
Do not place and we put like 80 something.
but as soon as we get close to the H equals 0.02, we see that those slopes are relatively similar. Of course, it's undefined when H is equal to 0. Now you might say, what if I want A to be different? Well, you can move A. Change A. When you change A, you change the slope of the tangent line. And then you can change the corresponding slope of the secant line as well.
Okay. Can you just screenshot or like send that to me somehow and then I'll just fill it all this out.
But the secant line always passes through that point A, F of A, and then some other point. We can let H approach 0 and we get that. Now, if we wanted to, we could also let H be negative because we could subtract H as well. So now when we let H vary, our points can be that second point x2, y2 can be either to the left of the original point or the right of the original point, but as H approaches 0, which is what we're primarily interested in, we see that the slope is approaching the slope of the tangent line. That's a little bit harder to see now if H is not approaching 0. I'll just use 0 there because it makes it easier to see. Now, if you want to, you can also change the code itself. You could just make this F of A minus H. And then everything with, and that would be A minus H as well. And then it would be easier to see. That way you can see that second point can go to the left of A F of A.
Either do one together.
But you can change A. Change the second point, and the second point always approaches the first. But the key is that the slope of the secant approaches the slope of the tangent. It's a little bit difficult to see, but that's the idea. Might actually be easier to visualize and understand if we created a table of values where we let H be, H could be 0.1 and then 0.01 and then 0.001, and we could find the slope of the secant every time and show that the slope of the secant approaches the slope of the tangent. That's usually how we do it in class. But hopefully this visual helps you understand the idea. And if you're unsure, if you're saying, I'm not sure I believe that, make a table of values, convince yourself that for different values of h, and as those h values approach zero, the slope of the secant approaches the slope of the tangent. And for a particular example where you already know the answer, that's always a good way to go.
And then just